So it's my pleasure to invite Joseph McDonald from the University of Alberta, and he's going to speak to us on the stone space of an orthomodular lattice.
All right, thank you very much. And I'd like to, before I start, I'd like to thank all the organizers for putting this conference on. I think it'll be very nice. So yeah, I just want to tell you about some summer research that I've been doing with my doctoral advisor, Kata Bimbo. Yeah, we've developed a nice duality for orthomodular lattices. So I just want to begin with a little bit of history. So talking more about just ortholattices generally, some of you may know that, well, in 1975, Goldblatt developed a nice representation theory for ortholattices using stone spaces. And he did this by equipping a stone space essentially with an orthogonality relation. My supervisor much later ended up extending this into a full duality for ortholattices. But when you want to study the representation theory of orthomodular lattices, it becomes a little more difficult, as Goldblatt showed in 1984, because he showed that you can't really characterize the condition of orthomodularity using a first-order property on the relation for orthogonality. And so this kind of raised a natural question as to whether or not there exists a first-order definable class of relational structures in which you can actually represent orthomodularity. And so this question was answered in the affirmative by Hartonis back in 2016, who introduced what he calls orthomodular frames. He developed a nice semantics for orthomodular quantum logic. And so the goal with our project is basically to topologize the ortho frames that Hartonis introduced and develop a nice duality based on this. Just a little reminder, an orthomodular lattice is simply it's an ortholattice, so it's a bounded lattice with an orthocomplementation. And it satisfies this condition down here. It's the orthomodularity law. There's a bunch of different equivalent formulations. And the canonical example, I'm sure as many of us know, arises in Hilbert spaces. You take the lattice of closed linear subspaces of an infinite dimensional Hilbert space, and what you get is an orthomodular lattice. And if you restrict the space to, or if you restrict your space to a finite space, then what you get is a modular ortholattice, which is subtly distinct. Okay, so here are the orthomodular frames Goldblatt introduced, Hartonis introduced. Kind of a long definition, but you have this underlying meet semi-lattice structure. And yeah, so you have a meet semi-lattice, you also have this orthogonality relation, and you have this distinguished subset, which I'll denote by omega. So we want to require that the meet semi-lattice structure has an upper bound, which we'll write by little omega. We have a few other conditions here. Hartonis refers to this as the orthomodularity axiom, condition 4 there. And if you look at some of these other conditions, you'll notice that this perp relation that I'm using isn't a strict orthogonality relation, because we can have some points that relate to themselves, and you typically regard an orthogonality relation as something that's irreflexive, right? And so I'll call this a quasi-orthogonality relation. But notice that if you take you take all of X and if you take the set complement of little omega, then what you actually get is a strict orthogonality relation. So that's what an ortho frame is. So here's just a little bit of notation. So if we start with an ortho frame, we'll say that a set is orthostable or perp stable just in case it's equal to the orthogonal complement if it's orthogonal complement, right? And then we'll let gamma denote the closure operator induced by Galois connections on the underlying neat semilattice structure, so that if you evaluate gamma at a single point, then what this amounts to, considering essentially, is just the point generated upset of the point x here in that case, right? So so we'll say that, and so this is a class of spaces that we introduced. And so, yeah, and we call them orthomodular spaces. So they're ordered relational topological spaces with an ortho frame reduct, right? We want to require that it's a compact space by C of a space, I mean the closed sets, and O of a space, I mean the open sets. And so CO of X upper dagger will be the Clopin stable sets. So we want to require that these be closed under taking intersections and orthogonal complements. This requirement number 4 is similar to a requirement that Hartonis has in his paper. We want to require that every Clopin stable can be written of the form gamma z for some z living in this distinguished subset omega, which is governed by these axioms that I just showed you. And then also we want to require that we have like this Priestley style separation axiom, condition 5, right? If x is not less than or equal to y, then there exists some Clopin stable containing x, but not containing y. And then we'll say that 2 points, or if 2 points are orthogonal to one another, then there exists a Clopin stable such that x lives in, or containing x, and whose orthogonal complement contains y. So these are the classes of spaces that we're working with. And these are the spaces that we want to show to arise as the dual spaces, or as the stone duals of the orthomodular lattices. All right, so here's our first lemma. So let A be an orthomodular lattice. Let's script f of A be the filters on A. Let P of A be the principal filters on A. And then we want to define this canonical representation map H, which takes an element and returns the set of all filters containing that element, right? And then you have, we want to define a topology via the subbases, right? You take the H of A's and you take the union of those with their complements. That's what I mean by minus H of A there. And then also we want to define this canonical relation. We'll say that two filters are orthogonal to one another, just in case there exists an element in the lattice that lives in X and whose orthogonal complement lives in Y, right? And so then the claim is that this structure, which I will denote by script S sub 0 of A, the claim is that this is an orthomodular space, right? The proof is pretty long, so I don't really want to cash out many details. For compactness, it uses kind of the similar argument that Goldblatt uses, and in his paper, it relies on Alexander's subbase theorem, and hence requires choice. And then we also have this nice corollary that, well, if you restrict the filter space, or if you forget about omega on the filter space, then what you actually have is a full orthogonality relation. And it's also easy to prove that this is a stone space because, well, it's compact, and by condition 5, it's totally disconnected. And so we have a stone space. All right, so now we want to give, the dual construction. We want to start off with an orthomodular space and see how you get an orthomodular lattice, right? So the result that this gives rise to an ortholattice is pretty easy. By definition, we're working with orthostable subsets, so clearly the orthogonal complementation is going to be an involution on the Clopin stables, right? To show that it's order reversing, that essentially just follows from the definition of orthogonal complementation and the symmetry of this relation. That it's this orthogonal complementation is in fact a complementation is also easy to show. And then the orthomodularity condition is really the only tricky part here. It falls out of condition 4 of orthomodular frames, which is condition 4 right there, and then condition 4 of orthomodular spaces. So now we know that if you start from an orthomodular lattice, you can construct an orthomodular space, and then dually, from an orthomodular space, you can choose a certain field of sets, and you get an orthomodular lattice. Now we have, we also proved this representation theorem, which says that, well, if you have an orthomodular lattice A, and then you take S sub 0 of A, which gives you a space, right? And then you take the algebra of its clopin stables, the A sub 0 of that space, then what you get is an isomorphism. And this can be proven simply by using this function h that we've defined in this previous lemma. And this it's not too difficult to show that what you get is an isomorphism. And what's kind of maybe not super surprising, but slightly different from a lot of representation theorems is that when you're h applied to the bottom element of the algebra, it doesn't give you the empty set, right? If you're working with, say, proper filters, what you'll get is the empty set. But if we're working with arbitrary filters, so you get actually the singleton set consisting of omega. And then we also have, I don't think this is a common term in the literature, but something my supervisor likes to call a so-called algebraic realization of a space. And so if you have an orthomodular space and you construct its corresponding orthomodular lattice, and then taking this operation on that lattice actually induces not only a homeomorphism, but a relational isomorphism as well. So what you actually get is a relational homeomorphism. So that's the object duality. But we want a full duality. There are some other known, say, representation theories of orthomodular lattices, but at least the ones that I'm familiar with, the authors don't go as far as to extend this to morphisms to turn it into like a proper, I guess, like functorial duality. But we do that here. So recall that, well, a homomorphism between orthomodular lattices is what you would expect, right? It just preserves the operations of the lattice. But the functions that we want to use to accompany the orthomodular spaces, we call continuous weak p-morphisms. So a continuous weak p-morphism is simply a continuous function that satisfies these following conditions. So these conditions on the frame are very similar to that of, say, a p-morphism that you get in modal logic, if you're familiar with that subject. The only distinction is that on the antecedent of, the consequent of condition 2, the right-hand conjunct, for it to be a true p-morphism, you'd actually want that to be a strict equality instead of this partial ordering there. So yeah, you could think of a continuous weak p-morphism as essentially, just a continuous function that's something like a p-morphism on the frame. Okay, so now we want to show how you could actually you could construct a contravariant or how you get contravariant functors between these categories, right? So if you start off with an orthomodular lattice homomorphism, if you define S sub 1 of phi, where phi is the homomorphism, and you define this to be the inverse, and you restrict its domain to the filter space on A prime, then what you get is continuous weak p-morphism from the dual space of A prime to the dual space of A. And hence by the lemma which assigns to every orthomodular lattice its dual orthomodular space, what we get is a contravariant functor, because of course the arrows become reversed, right? If you have a homomorphism from A to A prime, then what we're saying is that what you get is a continuous map from the dual space of A prime to the dual space of A. So it's in that sense, it's a contravariant functor. And so then we have this similar construction going the other way, right? If you have a continuous weak p-morphism between orthomodular spaces, and you take the inverse, and then we have this construction where so psi is a continuous weak p-morphism, and you define a sub 1 of psi to be the inverse of psi, and you restrict its domain to the algebra or to the orthomodular lattice of Popin stables of x prime, then what you get is a orthomodular lattice homomorphism from the dual lattice of x prime to the dual lattice of x, and hence a contravariant functor from the category of orthomodular spaces to the category of orthomodular lattices. It's pretty easy to see that, obviously the orthomodular lattices form a category, and it should be pretty obvious, I think, that the orthomodular spaces form a category, right? Because when you're defining the functions, like clearly you have the category of topological spaces, you have the category of, say, Kripke frames and p-morphisms, and so it's not too difficult to see that everything should work out there. In light of what we've shown so far, all that we need to now show essentially is that we have a nice correspondence, a nice one-to-one correspondence between the mappings, so it essentially suffices to demonstrate this equality. Recall that if you have S sub 1 of a homomorphism phi, this is essentially, or this is just the this is just phi inverse, right? And so this is a continuous function, right? And we also showed that if you take a sub 1 of a continuous function and you define that to be the inverse of that continuous function, then what you get is a homomorphism. And so that clarifies that point right there. And then similarly in the case of here. And so another way to view this is that these diagrams commute. I think this is maybe a nicer way of looking at that, right? Again, you could take the inverse phi inverse to just be a sub 1 of s sub 1 of phi, and then psi inverse, or the inverse of psi inverse. You could just take s sub 1 of a sub 1 of a continuous map psi, right? And so we prove that you get these equalities, and hence you have these nice commutative diagrams. So I think this is my last slide. I just want to maybe talk about a few future directions. I guess I have a little bit of time. Duality theory is kind of my main area of research, and I think it might be interesting to explore if this could be done independently of choice. This is very much related to some recent work of mine that I did in collaboration with Kentaro Yamamoto, who I think is giving a talk in the other room right now. Yeah. So we did this for ortholattices, and it's actually just came out on the Algebra Universalis website yesterday, and so we'd like it. But in this case, instead of using stone spaces, what we work with are spectral spaces. And instead of working with clope and stables, what we're working with are compact open sets. And so perhaps there's some way to kind of cast what we've done, what Kata and I have done here for orthomodular lattices in a choice-free setting using the spectral spaces that we were working with. And then also it might be interesting to see if one can develop some sort of topological semantics for certain quantum logics. I think that would be really nice too, and also explore maybe certain orthomodular lattices with operations. Maybe consider an orthomodular lattice extended by certain implication operators, such as, like, say, Sasaki projection, Sasaki hook. I think that would be cool to be able to maybe give a representation of those, of these structures. That's all I wanted to say, I think. Here's my references.
So I guess one quick question, one less quick question.
Mhm.
So the quick question is, when you're talking about these things as frames, I think I got confused. Is that frame in the sense of Kripke or frame in the sense of like a locale?
Yeah, sorry, in the sense of Kripke. Yeah, I maybe I should have just said a relational structure. Yeah.
Especially
Sorry.
if you're talking about caring about choice. So I just wanted to know.
Yeah, that's a good point.
Yeah, totally. And then, so you said that these things form natural semantics for some sort of quantum logic of some kind. The actual axioms that you wrote down, my eyes were incapable of not glossing over during that slide. So would you just mind giving some sort of an example of how these structures arise in the wilds? What quantum logic are they semantics of? Maybe that would also be helpful. Just, yeah, what do these things do?
Yeah, so I'll show you go back to yeah, so I don't know a whole lot about quantum logic, but the paper, you can find the precise, actually, I'll go back to the references. The precise system of quantum logic that is being studied can be found in Hartonas's paper right there. And it's just so he refers to this as orthomodular quantum logic. And in this paper, he describes it as essentially giving a sort of foundation or a logical foundation for infinite dimensional Hilbert spaces, right? It's like, if you look at the paper, it's a pretty kind of simplistic kind of natural deduction system, maybe like you might want to call it like a Gensen style natural deduction system. It essentially looks like classical logic, plus you have like this orthomodularity condition, but of course you don't have distributivity, right? So yeah, in the way that Hartonas goes about studying this is like once he constructs the canonical frame, like it's very similar to our construction, but he's just not working with the topology, right? So he considers like the canonical frame, or the relations on the canonical frame are defined in the exact same way. He's working with like the arbitrary filters, and he considers like a distinguished subset of the principal filters. And so there's some nice connections, and like the proofs in his paper kind of gave us some nice insights on how we ought to like construct our proofs, I guess. So, but yeah, it's a very nice paper, and so it's definitely worth reading. And you could actually see he lays the system of quantum logic that he's studying out. I don't know if this is a standard system of quantum logic but yeah. So
yeah, but I guess these axioms then come from the logic kind of came first, and these are just the things that make the semantics work out.
Yeah. So in that sense, they're kind of like artificial, I guess, as far as I could tell. Maybe there's a better intuition that I've just missed, but they seem to be fairly artificial in that sense. But it's just it allows everything to work out nicely, I guess. Yeah.
Thank you.
Yes.
So your duality is with respect to also modular lattice.
Yes.
The whole class, right? You can go back and forth. I was wondering, is modularity expressible as a first order property in your semantics?
Orthomodularity is
orthomodular, but the modular ortholattices are a proper subvariety, so
right.
The modular law in your semantics has a first order on the first order formula added to the frames that you have, so that they just give me frames of modular ortholattice.
That's actually, I don't know. We haven't tried working that out, but that's actually another kind of future line, like to study the modular ortholattices. My guess would be yes, but that's very much a guess. I certainly don't have any sort of proof of that, but.
There are lots of open questions about orthomodular lattices, and your duality might shed some light on some of these older standing problems.
Yeah, that's why kind of our motivation for studying these specifically is just a lot of people in many different areas seem to be very excited about orthomodular lattices and related structures. And so we thought they're nice algebras to study. Yeah. Thank you.
Yeah, so I was just wanting to see if you had looked into, there's this theory, this pretty recent theory from the coalgebraic logic perspective, where
Okay.
people have identified these relational spaces, topo-relational spaces,
Okay.
as coalgebras of certain functors. And a lot of these dualities end up being like expressible as a duality between like algebra and coalgebra of a certain functor.
Mm-hmm.
So I was just wondering if you thought about this from that perspective at all, or if
Yeah, I haven't looked into some of the coalgebraic aspects, but I do have quite a few like coalgebraic buddies that I would love to run this by. Yeah. Yes.
Very related question, actually. I noticed that your definition of morphisms in the orthomodular spaces,
Mhm.
they're like weak p-morphisms.
Yeah. Yeah.
So, I mean, are you considering these spaces to be kind of like simulation? That's like spaces up to simulation? Because
That's kind of a nice way to think about it, given this whole connection between, these modal, like kind of these functions that kind of carry these nice like modal properties in that sense. Yeah.
okay. So there's like some sort of Hennessy-Milner type theorem that's just waiting to be.
Oh, okay. Yeah. Right. Yeah. Yeah. Nice point.
Any more questions? Okay, make the last one because we've got to swap.
Yeah, I just had a question about whether you have looked at completions of orthomodular lattices and if you have any kind of representation of those in your, like when you look at dual spaces, regular ones, something like that.
Yeah, so we, in my paper with Kentaro, we look at things like canonical extensions and McNeil completions. We develop what we call well, it's not my term, it's I think Nick Basanishvili and Wesley Holiday. This is the first time I heard this term, that they developed like a nice duality dictionary, they call it. So we did the same thing for ortholattices, and we gave characterizations for the canonical extensions and McNeil completions. We have yet to develop this duality dictionary, but that's maybe something else we'd like to look at, because I think, but although the case with orthomodular lattices is slightly different, say with McNeil completions, right? Because you don't get closure under McNeil completions, where it's like with ortholattices. Is that true? Yeah, with ortholattices, yeah. So, yeah.
All right, well, let's thank the speaker again.